Ready to start. Kendra has a one announcement. As you approach lunchtime, you'll notice the round tables outside. They'll be all set up beautifully for lunch. Unfortunately, it's not your lunch, okay? So the idea is don't be picking from the tables, yeah? We'll have lunch in our normal manner. So when Giorgio does come in, would someone remind him to go and see Kendra? He has to hand in a travel announcement. Okay, over the past week, you've heard the word ionosphere repeatedly mentioned. So obviously it's important. How many of you would say you're familiar with the terrestrial ionosphere? Okay, so you individuals I'm going to look at when I ask questions. Okay, so that you can help the others by demonstrating superior knowledge. Okay, so I plan to ask them as I go along. So as you can see from, who am I? I'm this guy, Jan Sojka. The J's are pronounced as Y's, so it's Sojka and Jan, okay? I'm of Polish, German, Scottish extract, and I'm an American in principle, okay? Utah State University is where I come from, and there we have a center which emphasizes the word aeronomy. The upper atmosphere. So it's everything to do with the neutral gas and its interface to the plasma world that you've been hearing about. So an ionosphere is a very important interface between the plasma universe, if you like, and a habitable planet, okay, like our own. So let's just proceed. During the week, you've kind of heard about a number of reasons why the ionosphere is important. The last few lectures on impacts to society have been brought up. The electrojets that we heard about yesterday most certainly cause problems. How many of you have ever used a GPS handheld anything? Oh, I'm surprised. Good. Well, these GPS devices today allow you to drive your car to desired destination with no trouble. Of course, that's not quite true for a number of reasons, but we'll be talking about that later on too, how something as simple as the ionosphere and the GPS system interact very closely, especially during disturbed times. You've heard about the power networks and grid systems, how they're sensitive. Satellites, the Air Force is really concerned that it always knows where all of the objects in space are in case new ones appear unexpectedly. Well, after a major storm, a geomagnetic storm, all of these appear to be in different orbits by an amount that makes tracking and recovering all of these orbits difficult. And that's, again, part of the Ionosphere-Thermosphere. Unfortunately, these two words are linked. There is no ionosphere without a thermosphere as far as our terrestrial planet is concerned. So let's kind of move into the first kind of... that's strange already. This sentence here is gone. Robert Shunk, that you don't see here, and Andy Nagy created a book called Ionospheres, and it's a Cambridge Press book. This is where, if you want the most current graduate level reference for the ionosphere, this is a proper book to go look at. The lectures, of course, come from the textbook. Particularly, Professor Tim Fuller-Rowell gave a lecture very similar to this one, and I'm indebted to him to a large extent. Many of the view graphs you're going to see are from him. Okay, so let's move on. Let's hope. Okay, this is much better. So a neutral atmosphere is the first thing we have to worry about. Down here on the ground, what's the composition of air? Oxygen, nitrogen. Okay, what's special about oxygen, nitrogen? What's the ratio approximately? 70% nitrogen, and it's molecular nitrogen, and the oxygen, is it atomic or molecular? It's molecular, and now we breathe this. What do you think the composition is at 100 kilometers where we enter the ionosphere? Aha, surprising, it's the same. Okay, and of course there's some other things in there that eventually become dominant. And we'll talk about that in a minute or two. But our air down here is nitrogen, oxygen, And even at 100 kilometers where we're into the ionosphere, it still is. And there's a number of interesting attributes we'll talk about. Okay, so we need to have this thing we call an atmosphere. And as it enters this region where ionization occurs, and we'll talk about the source of the ionization, we start to change the nomenclature. So let's put up a figure that shows this in gory detail. This is still the atmosphere, and this is atmospheric terminology. These are our layers. I'll point out a number of words. The troposphere, stratosphere, mesosphere, and this then the thermosphere you've heard mentioned during the week. But there's these things called pauses, the tropopause, the stratopause, the mesopause. And things happen at these places. And here's an altitude scale. Here's our 100 kilometers, which is a good reference number to remember. Things happen from there up with a few kilometers down. But basically, what we talk about as the ionosphere exists from about 90 to 100 kilometers all the way up. And at some point up here, as we kind of run out of what you might call O+, the primary ion for the ionosphere, we start to enter the exosphere, and eventually the word magnetosphere takes over. But there is no clear line drawn up here. But down here, the lines are a bit clearer, and composition is a big deal, and we'll be talking about that. This is schematically indicating the altitudes over which the auroral emissions occur, between 100 and 200. We saw Eric Donovan showed rather gorgeous movies of the aurora, and these occur at these kind of altitudes, but not globally all over the place. The temperature down here, what's the kind of daytime temperature down here? Down here in the troposphere, what's our typical daytime temperature? Does nobody know? 300 Kelvin. And plus or minus, how much can we withstand? Plus or minus 50 maybe? Yeah, so okay, so we kind of know this down here has a little wiggle to it as far as we as human beings. But up here where we are, the temperatures are significantly higher. How many EV is 1,000 Kelvin? Sorry? 0.1, that's correct. Now 0.1 EV compared to any number you've heard in the last week, is it large or small? It's totally irrelevant, you'd almost argue, okay? So the temperatures that we are talking about here are tiny. The aurora is the one place where energetic particles, electrons or protons or other ions come in and create the aurora. And these are kilovolts all the way up to MeV, depending on what you're looking at. Okay, so that's your neutral gas. It's kind of special up there in another way. Here is what we've talked about, O2 and N2. Here's our concentration per centimeter cubed. These are the units here. And here's our altitude coming up through. Here's your 100 kilometer mark. And this kind of normal atmospheric composition is still dominant. But you notice what's sneaking in here. O, just neutral O. What can you tell me about neutral O? What's special about O, oxygen, atoms, not molecules? Chemically, what do you attribute? What properties have they got? What does oxygen do very easily in this state with anything else it comes in contact with? It oxidizes. This, in terms of long duration exposure in space, satellite surfaces have to be chosen very carefully that they don't overly interact. NASA's flown long-term missions to study the degradation. You normally think of high-energy particles beating on satellites and causing disruptions, spacecraft charging, and other things, ablation even. But the environment it's in is relatively up here, 140. As you keep on going up, as you'll see in a minute, you get into a region that's very rich in just atomic oxygen. So chemically, it's a kind of difficult environment to be working in. Okay, so let's move on. This introduces a region where the atmospheric composition changes dramatically. At this point here called the turbopause, Here's 3 different scenarios. 112 kilometers, 105, and 94 models suggest how things change. Beneath this point at the 104, 100-ish kilometer mark, the composition stays constant. And that's because it's well mixed, turbulent mixing. So this gas where we are, where we breathe, stays in its fixed composition ratio. This plot is a ratio of argon to N2. It's just an example. And 1 doesn't mean there's as much argon as N2. It's just a relative scale. But as you go higher, beyond this point, the species separate out. And they separate out on their own hydrostatic equilibrium scale. So that's kind of important. Again, it comes back to this 100-kilometer mark. As you kind of go upwards, the atmosphere, the thermosphere as we call it, is quite rich. Here's our N2 and O2, but as you can see, O has already taken over, and light ions eventually are very important at higher altitudes. So our neutral helium and hydrogen start to appear significantly. Why are helium and hydrogen apparently increasing in abundance at these higher altitudes relative to the other atoms and molecules? What's the process that leads to this change in the composition? Okay, it comes back to our hydrostatic equilibrium. Okay, you have a scale height associated with, what does a scale height depend on if I tell you all of the species have the same temperature? The mass, okay? And of course the heavy ones end up with smaller scale heights, so they fall off more rapidly with altitude, and the lighter ones. So this kind of is very important for how the ionosphere is going to develop. Okay, just before we leave the neutral atmosphere, the thermosphere, this is Mars as an example. It also has an atmosphere, and right away you can see that the species that you're familiar with appear here too. Here's your O, your O2, N2, and in the Martian case, it's a bit more complicated. Our kind of greenhouse gas, CO2, and there's some CO and NO exist. We'll come back to CO2 and NO a little bit later on because they are rather important. Oxygen, again, is dominant at the higher altitudes. The very lightest atoms, helium and hydrogen, have all but gone. Okay, so now we can talk about the ionosphere. Well, the ionosphere, it exists in our neutral gas. The relative plasma to neutral density is variable, and fully ionized versus partially ionized are fairly common words. As you go lower down, the fraction of the plasma is much smaller, and it's collision dominated low down, and it's a collision less. We have to be careful when we say that, whether it's collisionless or how collisionless and what processes aren't existing. So we'll have to talk about that later on too. The dayside plasma is produced by solar EUV soft X-ray ionization. It's our primary way of producing an ionosphere, and we'll spend some time on that. Then we'll talk about how this is electrically coupled to the magnetosphere. Through the week, with substorms and even just reconnection and setting up magnetospheric current systems, they all close somewhere. And one of the fundamental areas where the close is in the ionosphere, so that by producing a plasma, we also have electrical properties that are important. Okay, now in the terrestrial case, we have this very strong magnetic field, and we'll talk about that. That controls to a large extent how the magnetosphere and ionosphere kind of interact. Okay, so this is our first slide of the ionosphere, and we'll spend a bit of time on it. The density scale here is logarithmic, 3 orders of magnitude. Here's our 100 kilometers again, the reference point. Although this line cuts off rather sharply, depending on solar flare conditions or in the high latitudes, very energetic particles from the sun or cosmic rays, you can get some residual ionization to much lower altitudes. And they are, as you'd expect, very high energy particles and have other problems associated with it. But our typical day region is below this 100 kilometer mark. At about 108 kilometers in here, there is a peak, and that's referred to as the E region peak. If I jump up a little bit, somewhere around 300, 250 to 350, depending on where on the Earth you are and what processes are working, is what's called the F region peak. But more properly distinguish it from the F1, it's called the F2. So we have this nomenclature, D, E, F, to represent our layers. The layering is really two good layers, an E layer with a peak, which is made up of molecular ions. The F2 peak, if you like, is O plus ions, and as you go higher, there's no peak, and there's not a third peak up here, but the composition changes dramatically to our light ions. These helium pluses and hydrogen plus represent this curve here. This curve, the solid line, in fact, is the electron density. Charge neutrality exists so that you sum up at any given altitude all of the ion species, and that then represents our electron profile that you see here. The ionosphere has been labeled here, and the protonosphere is labeled up here. It's in the neutral gas, it's called an exosphere. So the nomenclature just keeps on adding more and more layers. The plasmasphere from 1,000 kilometers at low latitudes exists, but we won't go there today. What the takeaway message is here is the lowest significant layer as far as coupling to the magnetosphere is called the E layer. It's made up of molecular ions, and that's where the conductivity is. You heard about the Cowling conductivity. Well, we talk about three conductivities: the Hall conductivity, the Peterson conductivity, and Birkeland along the field line currents. So down here, this is where the currents close. Up here, O plus is the dominant ion, but it's also the point at which the electron density maximizes. So all of our GPS problems arise primarily from this part of the ionosphere. Okay. If I spend a second or two on the F layer, the dominant layer, if you like, the physics and chemistry are kind of straightforward. The top here you see is pretty much a scale height kind of curve. It's a logarithmic in density and linear in altitude. So we have what's called diffusive equilibrium is this property. Underneath, where the neutral density is much higher, you have the kind of chemical equilibrium curve. So that over here there's a transition around the peak between diffusion becoming important and below it chemistry. And chemistry just means the production source is being balanced by the losses. So down here, it also is generally true that the time constants for this chemistry is much faster. At our lowest altitude of about 100, the time constants for things to come to steady state, if you like, are under a minute. And when you talk about solar flares, this bottom region would respond to the time scale of flares. This is not true higher up. The time constants up here for the diffusion process to couple in is tens of minutes or longer, depending on if it's daytime or nighttime. Okay, so that's kind of a bit more of our background. Who sent the first radio waves, radio communications to America, or the American continent? Marconi. Where was Marconi located when he sent these radio waves? That was the reception area, Newfoundland. Where was he which country or which continent even? Europe, okay, and if it's with Europe, which country in Europe was he in? England, okay, so basically from England, is there a straight line communication path to Newfoundland? Okay, this is 101, this is pretty straightforward, guys. Okay, so how did the radio wave get to America? That's right. So the ionosphere right back then at the turn of not this century, but the last century, was found to be a good reflector of radio waves. And that brought us into what you might call the modern day, an age of being able to measure things about the ionosphere. So when you're reading literature, so that's what the purpose of this is, to familiarize you with one other aspect of ionospheric research. We interchange between the word density and frequency. And the relationship is the plasma frequency, where F squared is proportional to the density. The radio frequencies from about less than 1 megahertz up to about 20 megahertz represents the range over which the densities in this layer kind of exist. So this diagram may seem nowadays a kind of older diagram of representation of the ionosphere. This axis is the plasma frequency. Radio waves, when propagated vertically up from the ground at a particular frequency, if let's say this is 10 megahertz, if you propagate up at 5 megahertz, it will come to a point at which in the ionosphere the local plasma density is equal to 5 megahertz. At that point, the radio wave, to put it simply, comes back. There's a reflection, to put it extremely simply. But nonetheless, this entire regime was studied using radio waves. So it's a remote sensing, it's not an in situ. So most of our early knowledge of this ionospheric shape came from radio waves. And hence the nomenclature, FOF2. So the F2 you've come across. What does FO represent? The frequent, it says it's the O I'm trying to see if anybody is familiar with. FO represents the ordinary ray. In radio propagation and magnetic field, it's very important to distinguish between the extraordinary and the ordinary propagation modes. And this FO means that they've actually identified the ordinary, and the ordinary one is the one that's directly related to the local plasma density. When you transmit, you can also get the extraordinary propagation path reflecting. And that's why ionograms are often very confusing, and you don't get very easily interpret signals. But this nomenclature comes from this radio world. HMF2, again, is the height of the maximum frequency. In an ionogram, no radio waves come back from this area here. Once you reach this critical frequency, there's no information about these regions where the density gradient is decreasing. Down here, we have the same idea. This peak here is the E region peak, and of course, this is the ordinary radio wave path, if you like, propagation path, and this is the height. Inferring the height is a non-trivial task because the radio wave retardation is an integral through all of this electron plasma it's gone through. So it's very important when you're talking about ionospheric region and comparing with old papers and whatnot. Plasma frequency is used as a one-to-one representation of the electron density. The height is very difficult to use. It's called a virtual height. It's a propagation time, and it's got delays built into it due to the retardation the radio waves receive. Okay, the other very important aspect of the ionosphere is how the temperature changes. There's 3 different temperatures, put it simply, although it gets more complicated than that even. The first one is the neutral temperature. So this neutral gas in the thermosphere has a particular temperature. S min, what do you think S min versus X max refer to? Solar minimum, solar max. So under solar minimum conditions, here's our temperature scale. The thermosphere is under 1,000 Kelvin. During solar max, the neutral gas is heated up, and that's reasonable. Then we have the ion temperature. The ions are pretty much, for most of the altitude range, collisionally coupled to the neutrals. So their temperature is very similar to neutral temperature. The electrons, however, are different. The electron gas both has a volume heating and through conduction from higher up can be heated. Plus, when photons come in on the day side and ionize, these photons have residual energy. So the electron gas automatically has a heat source. So the electron gas temperature is different from the ion temperature. You heard during the week often conversations about T parallel and T perpendicular, where depending on the magnetic field geometry, you can have different temperatures parallel and perpendicular. In the ionosphere, under extreme heating conditions, this is very common. And as you go to the top of the ionosphere, it's even more common as plasma, called the plasma wind, outflows at high latitudes. then you can have significant differences in parallel and perpendicular temperature. Okay, I have here a little complication. On this axis we have height, and you can see it looks kind of logarithmic. Here's your 100 kilometers, and here we go up through the ionosphere. On this axis we have the pressure levels, and this pressure level scale is a very natural one for the neutral gas. So in our field, again, not only do frequency and density get interchanged, but when you're looking at diagrams and even contour plots, it's very important to realize whether the writer has used true altitude versus pressure levels. Okay. So Mars has an ionosphere. We said it had a neutral atmosphere, so it's not a surprise it's got an ionosphere. So again, the things we're looking for are here. Here is O+. In here is, this is CO2+. Here's O2+. So here's a question. What would you call this layer using terminology from the terrestrial world? It's the largest peak is O2+. What layer is that in the terrestrial world? Is it the F layer? Okay, what's my alternative? If you use composition as your guide, what would you call this layer? This would then be called an E layer. Our E layer in the terrestrial ionosphere is dominated by molecular ions. So on Mars, it's the molecular O2+, which is the dominant ion. O+ over here, although it's kind of trying to form a peak, it's still shadowed, if you like, by O2+. Okay, so now I'll go into a number of the processes that lead to the ionization that we've talked about. Okay, the first one, of course, the key one on the day side is solar EUV radiance. And the recent NASA SDO satellite with one instrument that we haven't talked about. We've talked about the AIA instrument and the beautiful imagery. You watched the Venus transit on it using imagery from that satellite. But in addition, there's a spectrometer, an EUV spectrometer that kind of collects data that represents the ionization source for the upper atmosphere. Okay. Historically, if you like, there's this timed satellite with an instrument called C and our SDO EVE instrument. These two instruments are spectrometers, and prior to their flight, only rocket data was kind of readily available. And rocket data, how long does a rocket flight last? An hour? More or less? A few minutes. 15 minutes if you can get up to 800 kilometers. But most rocket flights are significantly less. In terms of looking at the climate or even a flare, what can you tell me about the difficulty of 15 minutes? That's right, you'll never see one, okay? So that until we got these kind of 24/7 type satellite observations of the solar spectrum, we were very challenged as to how to represent the irradiance in the ionosphere. And most recently, even though we have these, we suddenly realize how sensitive different layers in the ionosphere are to these different wavelengths. So the wavelength spectrum I'm talking about is from about 2 nanometers. How many angstroms is 2 nanometers? 2 nanometers, how many angstroms? 20. Okay, come on guys, we can do better than this. Okay, the reason I throw this at you, again, to confuse you thoroughly, people in the ionospheric world talking about the sun, talk about nanometers, but people on the sun, well, they aren't on the sun, but people who study the sun still use angstroms. There's nothing wrong with it, but it just causes more confusion. It's another interchange of 2 units. And the factor 10, in astronomer's sense, is negligible, so that the ability to confuse these two is high as well. So we work from about 2 nanometers up to about 120, okay? That's our kind of region that is very effective in ionizing, okay? But in terms of the thermosphere, you can go up another 100 nanometers easily for the major heat source for the thermosphere through absorption rather than ionization. So that's kind of the area that we're interested in. Of course, this solar flux, as you know, this irradiance, isn't constant in time. It varies. And this is a very crude picture, sunspot number that you've heard about. Along here, there's a rather exciting gap for us ionospheric types. When the sun went quiet, this number may have gone to 0, but the flux never went to 0, as you obviously realize. But all the proxy indices that we ever used in any earlier solar minimum were not representative of the flux we got during this time. So in the last half decade, we've had this rather exciting time of very, very quiet sun irradiances in our part of the spectrum. I put this up only because I'm embarrassed by it, but I admit my embarrassment. This is a very poor slide. Yesterday, you'll remember David Butler did have a nice plot of this. This is from 1860, if you can, it's actually earlier than that, from 1610, an attempt to reconstruct the solar cycle via the sunspot number. And the only reason for showing it is that if one tries to do kind of historic ionospheric archaeology, going backwards in time, what was the ionosphere potentially like? This record is one of the few that you can use that you might argue does indicate what the sun's irradiance was on the ionosphere. Things like the Earth's magnetic field has changed as well, and that would be very important. But the irradiance as given, as you map it from that, is very important. Unfortunately, even something as simple as the EUV and the soft X-rays, as far as modeling, one could argue one knows the neutral gas at a particular location, therefore it's straightforward. You have a cross-section, you have your photon flux, you just calculate. But in actual fact, there's a number of ongoing issues in our community that we haven't got all this information down pat. The issue here of photoionization, photodissociation, that's straight up chemistry, you would argue. We're good there. The idea that if you have a 2 nanometer or a 4 nanometer photon, its energy is many hundreds of electron volts. Ionization, as we heard during the week, is only a few electron volts. Hence, we produce photoelectrons with large enough energy either to escape or to produce other ionization or further ionization. This one box on its own introduces the first significant complication. If you're in the E region where it's collision dominated and you've got molecular ions, this process alone doubles the ionization rate. Now, we use rule of thumbs like factor 2, not 2.111 or anything like that. We just use a straight up factor. So even something as simple as the ionization from these short wavelength, very energetic photons leads to a computational nightmare. Okay, then over here, all of this feeds into chemistry, excited state chemistry. The excited states have different cross-sections for reactions. So the rate at which you actually move the chemistry around to produce other ions is dependent on how excited or which excited state you're looking at. Again, another kind of nightmare. Air glow, or from the neutral gas, losing energy, if you like, through air glow. I haven't even included auroral processes here. There's a little box here that says incoming particle flux. You could review that, you can regard that as the Aurora or something. But this entire kind of box or boxes define, if you like, how complicated it is to just come down and get the final energy in up here to electron heating, ion heating, and neutral gas heating. All three lead to the altitude profiles we showed earlier on. And we haven't yet built an ionosphere. We've just looked at one process, okay? So what other complications are there in something as simple as sunlight hitting the upper atmosphere? Okay, again, it's common sense to a large extent. Sunlight comes in, and depending on the local time of your location that you're interested in, you have what's called a solar zenith angle. This is your nadir straight up, but the sun isn't above you overhead unless you're at the right place on the, not even on the equator, but at noon at the right latitude, depending on season. This parameter, called the solar zenith angle, really controls how much flux or irradiance eventually gets to the point you're interested in. And that leads to a number of complications, if you like. So these profiles are production profiles. The production rate of the ion that you're looking at. One, it's normalized to the maximum. And the idea here is simply to kind of, from a reference point of view, Z minus Z max divided by the scale height. H here is the scale height. But what you're seeing is, depending on the solar zenith of your location, the primary ionization occurs at different altitudes and different intensities. And this pretty much drives the E layer very simply. So at dawn and dusk, the ionospheric E layer is higher up. By the time you come to noon, it's lower down. So when we say the E layer is 100 kilometers, it's much more complicated than that. And this is just allowing for the idea that there's an atmosphere that's absorbing all this radiation before it gets to you where you're looking to do your ionization. Okay. These are examples of observations. I haven't talked about the observations per se yet, but the primary way in which we observe the plasma parameters of the ionosphere as a function of altitude is through an incoherent scatter radar, not an ionosonde. An ionosonde only determines things like a Doppler drift. You can get the Doppler information, that's the velocity, and the density. But an incoherent scatter radar is able to send up a megawatt of power at very high frequencies. And the incoherent scatter, the Thomson scattering, if you like, that comes back, enables scientists to reconstruct electron temperature profiles, density profiles, velocity profiles too. Okay, so that's our primary tool, if you like. So here is our ionosphere. There's two examples shown here, the electron temperature and the ion temperature, which the instrument can measure. And then through modeling inference, the neutrals aren't, the temperature isn't measured by the instrument, but through inference, specifically down here, what the ions are doing, you know fine well down in this collision-dominated region, the neutrals are at this temperature. Okay, so these are just examples that we can actually measure these things. The auroral is then the space weather contribution. And Eric Donovan showed beautiful examples of aurora, so I won't show any more. We'll talk about it instead. The magnetosphere generates ionization via energetic particles, usually electrons, but it's not uniquely electrons. Oxygen, if it's there, can be deposited into the upper atmosphere. And protons, of course, are the other source. And these can be energized. And in the conversations you heard about substorms and others, the region between the ionosphere and the magnetosphere, or the more distant magnetosphere, is a very challenging region, because in that region there are other acceleration processes that we haven't even talked about this week. It's not reconnection, it's not a shock, it's kind of wave-particle instabilities. Anomalous resistivities are the kind of hand-waving terms that are used, and different attempts have been made to quantify these. But somewhere between these two regions, energies of 10, 15 kilovolts can be added to electrons as they stream into the upper atmosphere. And this is our auroral ionization. Okay, this is kind of the ionization, and we've seen that the consequence of all this electrodynamics between the ionosphere and magnetosphere leads to these auroral displays. And there's no doubt that the auroral display is the most beautiful aspect of geomagnetic storms. Scientists might feel that just having extra work to do and new funding as a result is great, but for the regular public, being able to see the aurora. How many of you have seen the aurora? Okay, it's pretty pathetic, isn't it? You guys should insist that we hold this up in Alaska, this meeting, so you can actually go and see the aurora. Now, during the summer, it's not so good. You know, why won't you see the aurora in the summer? Yeah, there's sunlight, and there's, yeah, it's kind of, the ionospheric physics is really easy, guys, yeah? Okay, let's continue, okay. Here is one of the biggest bones of contention in the literature. When one builds an MHD model of the magnetosphere, one has to close it out at the ionosphere in some way. And often it's done at 3 Earth radii or some unreasonably high altitude. In that way, MHD doesn't have to worry about the particle acceleration. But even then, they still have to introduce some form of resistor, Hall-Peterson conductivity, to close out. It's a boundary condition on the magnetosphere. But as the years have gone by, we're becoming more and more sensitive to the fact that this resistor is a dynamic resistor. It's continually changing. So a sophisticated MHD model requires the ionosphere to respond. So for example, what that means is if suddenly there's a huge auroral display, that means the flux of incoming electrons has increased dramatically. A consequence of that is that the ionization has increased dramatically, which means your Hall and Peterson conductivities have changed. In changing these in MHD terms, changing the conductivity rapidly launches more alphane waves. The MHD model loves alphane waves, and the subsequent interaction in the model leads to a compromised new solution, if you like. So this is where, in terms of electrodynamics, the biggest present-day problem is. How accurately can you represent the dynamics of this in this global scale model? And the problem really is grid resolution. You saw the kind of auroral dynamics that Eric showed. These structures are all subgrid on any global MHD model. So the actual details of how the auroral arcs change, the ionization leading to changes in the MI coupling are kind of beyond present day models. But people are working towards that. When we say the auroral electron fluxes, the precipitation, that's the word we use, precipitation. What is it doing? Okay, here are a sequence of profiles, and these represent the ionization rate. So mathematically, it's generate an ionization rate for O plus or N2 plus, and this is just a generic curve, if you like. What it tells you is that the more energetic the particle is, the particle energy, KeV, 100 kilovolts, 40, 20, 10, 5, 2, the deeper it penetrates and it deposits its ionization at different heights. And that's kind of important too, because the conductivity layers are sitting here somewhere. So very energetic particles, almost the MEV type, pass almost through our upper ionosphere E layer and do damage down here where the D layer is. Even, unfortunately, at altitudes where high altitude airplanes are flying across the polar caps. So for us, 100 kilovolts tends to be kind of the upper limit that this part of the ionosphere cares about. But the 5 to 20 are the normal ionization particles that cause the aurora. And by and large, these have the largest fluxes in this magnetosphere-ionosphere system. Okay. 2 electron volts sounds kind of no big deal, and you can just about extrapolate that as you reduce this energy to a kilovolt, 500 EV, it goes higher up. It turns out that as you go higher up, that ionization contributes primarily to the Pedersen conductivity, whereas the Hall is locked down here. And that difference becomes important too in the electrodynamics that's possible, or the solutions electrodynamics finds. Okay. This is just an example from an observation of how the quiescent TI curve here, and during an auroral event where the radar is looking, if you like, in a region of space that suddenly a bright aurora falls in. So the first thing that happens is that the electron temperature takes on a particular enhancement. So it doesn't look too large, but this is the kind of default electron temperature. Here's 2 times when 2 measurements were made. But the earlier pictures we showed, down here at 100 kilometers, The electron temperature starts off with the ions and the neutrals and then breaks away. But during auroral times, this might be 20 to 40 kilovolt electrons coming in. The electron temperature is heated up. Here it's 2,000, but it can readily get up to 3,000, 4,000. So it's still insignificant compared to MeVs or kilovolts. It's still less than an EV. But when you change the temperature like this, the immediate reaction is that the collision frequencies change. The chemistry changes. They're temperature dependent. So although this might not look too big a deal, 1,000 Kelvin is still negligible. In terms of chemistry, it's a big deal. This is the result of the auroral ionization. It's enhanced the electron density. Okay. Now we'll kind of go on to the next kind of major driver in the ionosphere. It's a combination of two things. Neutral winds. In the thermosphere, it's a very dynamic system and the neutral gas is moving around. And these are just hand-wavingly referred to as winds. The electric field, okay, so we've talked about electric fields before. Basically, the magnetosphere couples to the ionosphere, and there were discussions about how do you map from one to the other. And the basic assumption is that the magnetic field, if you like, between the ionosphere and the magnetosphere is a perfect conductor. So the electric potential maps down it perfectly, okay? And that's kind of one of the major issues that we have. Understanding the dynamics of this. During a geomagnetic storm, this changes immediately. But the winds follow, but later, maybe half an hour, 2 hours, 3 hours. Energy comes in to the upper atmosphere at high latitudes or wherever the aurora is, and the winds gradually build up as a result of this pressure bulge, if you like, from the hot gas. But these electric fields are responding directly to what the magnetosphere is doing. Okay, so that introduces a dynamic time constant dependence. Okay, it modifies. Oh, the other little thing we didn't say. The ionosphere actually co-rotates. Low down where it's collisional, the neutral gas is most certainly co-rotating with the Earth. Co-rotating in the frame of reference of looking at the sun and then in that coordinate system every day. It's not quite 24 hours, but the Earth turns, and in that turning, the neutral gas turns, the thermosphere turns, and because of collisions in the magnetic field, there is an effective description, which is an electric field called a co-rotational electric field, which, depending on the frame of reference you're in, we would argue exists and drives the low-altitude plasma. But because the field lines are conductors, that also drives the whole ionosphere. Okay, E cross B is our primary way of moving plasma around. How many of you can figure out an E cross B vector? Okay, 1. Come on, guys, 2. How many of you have a right hand? Okay, so here's a simple thing, just to see how easy ionospheric physics is. Okay, so you're at the equator, okay, and what does the product E cross B produce? I know it's not quite full, but what are we referring to? What happens in a plasma? What's going to happen with the E cross B? We've heard this in several talks. What does this generate? It's a velocity, okay? And the direction of the velocity is what's important. So if we have an E and a B, and if I tell you what the E and the B is, you can tell me what the velocity is. Okay, so here's the experiment, okay? You've got your right hands. You're at the equator. Which way is the magnetic field pointing above you? North. Okay, good. So that's our north direction for B. And if I tell you at the equator, the time we're talking about, the electric field is pointing to the east. Okay, so that's 2 of your vectors. So you get 2 fingers moving. Which direction is the plasma E cross B forced to go? Does everybody agree? You think these 2 guys are right, therefore you're agreeing, yes? How many of you have used your fingers? Okay, but that's the essence of a large number of things. At the equator, this phenomenon leads to what's called the Appleton crests, and we'll come to that in a second. But the idea that in our coordinate systems or in our ionospheric world, it is a totally reasonable thing to do, combine electric fields imposed by the magnetosphere or by dynamos in the atmosphere to produce the motion of the plasma, okay, using the E cross B. Our B field we heard the other day, no matter how large these currents are, very rarely changes by more than 1 or 2%. Okay, so the B field, to all intents, is our natural grid. Okay, I said the B field is this nice grid. What's our 0th order description of the Earth's B field? What do we call it? A dipole. But it's not a really good dipole, to be honest with you. Up here is a kind of map of the magnitude of the B field. Now, I don't need you to read any of these. You can see their contours. If it was a true dipole, what would you expect to see in this diagram? Yeah, just 2 sets of contours. But you don't. 1, 2, 3, 4, maybe a little bit over here too. So in actual fact, it's not a good dipole. But to all intents and purposes, we modelers of all sorts still use the dipole approximation. Now, the most sophisticated models today have gone over to models like this. Down here is called the South Atlantic anomaly, where the B field strength is relatively weaker than it should be. For a dipole, where do you have the largest magnetic field at a given altitude? At the poles, yes. And the pole has the largest B field at a given altitude. Where is the weakest? At the equator. And what's the factor between the two? 2. Okay, the polar magnetic field is double that at the equator. And these simple rule of thumbs are good, except if you're doing detailed work. Over here, where this B field is very weak, you heard about the adiabatic invariance, the bounce one. Okay, unfortunately, at this end of the field flux tube, if you like, and this one, there's a significant difference in altitude at which these 2 B fields are the same. So it's conserving that adiabatic is a difficulty. Down here, what happens is it's lower in the atmosphere than at the other end, so that what you get is preferential deposition through collisions, if you like, of ring current, not ring current, radiation belt particles. This is a kind of dangerous area for satellites. The radiation field here isn't too good. Okay, so that's kind of a little sidestep, but all of this is important because we said E cross B. Now, if B is not a nice homogeneous dipole, we have variability already. And present-day analysis of old records indicate that, hey, as the B field has changed over the last 100 years, our records from ionograms and others have to be interpreted somewhat carefully. The reason people worry about 100 years ago and 50 years ago is climate change. What did the ionosphere look like? If we knew what the ionosphere looked like, do we therefore know what the upper atmosphere looked like? And is that a telltale kind of flag about what the atmosphere is doing? And that chain of reasoning, if you like, breaks down because this picture is A, not a dipole, and B, isn't static. It's changing over time. Okay. The lower picture we won't go into. It's called the declination. The B field has an inclination, but also how far out of what you might call a magnetic dipole meridian that field lies. And this introduces not complications, it just makes it a more rich and more interesting driver, if you like. Okay, here's the 2 processes, why they're so important. The green line represents the magnetic field. Latitude's increasing this way. So there's 2 properties. The wind is one of these processes we talked about. The wind is continually dynamic. But as it collides with ions, the ions are restricted to moving along the field line. They're gyrating. So their gyro periods are better or larger than their collisional periods. So although there's collisions, they're still forced to move around it. So if you try to push this way, push is a very simple term, but one I think understandable. It has a net effect that it lifts or pushes upward the ions it's just collided with. And that leads to a vertical kind of drift. Clearly, if the wind reversed and goes this way, it would push things down. And similarly, the electric field. Most certainly in the ionosphere, the electric field is perpendicular. When I say electric field, it's a relatively DC electric field we're talking about, where time constants are much longer than 10 minutes or something. It's a relatively DC electric field. So the electric field is always perpendicular to the magnetic field. We've talked about that in many lectures. So you have a drift. And depending on the orientation, the azimuthal orientation of that electric field relative to this B, you have an E cross B drift velocity which is not horizontal, which means there's an effective lifting in this particular geometry we've shown. Is the electric field pointing into the board or out of the board with this nomenclature? Out to the board, right? Okay, we're just making sure we're all seeing it the same way, because you could use your right hand very quickly to verify it. But okay, so both of these lead to upward drift. Why is the upward drift so important? What does it do? Okay, let's bring up, oops, not that, I want to go to the, oh, I've lost it. Okay. Okay, well, we'll stick back with this one. It shows, in effect, the same phenomena. Earlier on, we talked about our E cross B at the equator and how we got vertical lift, if you like. So here's our vertical lift. This coordinate system from here, this is the equator, and here's our altitude range. Here's our ionosphere. This is magnetic latitude, if you like. And at the equator, there is this upward lift that lifts the plasma up to higher altitudes. However, the electric field, as you go further away, is no longer lifting. And this plasma that's elevated, if you like, has to fall back down. But to fall back down, it's stuck to the magnetic field lines. So now, as the electric field is less effective, its motion now turns into a kind of gravitational pull. But again, it can only flow, if you like, along the field line. So again, it's constrained. Here, E cross B allowed it to cross the field lines. It gets to a certain height. It can't just fall back down. The plasma must move down. Okay, so this is all sunlit, let's say. You have this flux now, plasma flux to these higher regions. And this leads to our first phenomena, if you like, in terms of the ionosphere. It's called the Appleton crests. Those of you who live in the equatorial regions may not know it's there, but there's a very strong density gradient with latitude. Here's our latitude, south to north. Around the equator, there's a minimum where the layer has been lifted to the highest points. And at either side, as the plasma flows down along the field lines, you have enhanced plasma densities. These numbers are a log, here they are, log density in cubic centimeter. So 10 to the power 6 on either side, and in here it barely reaches 10 to the power 6. So this phenomena was found pre-IGY, pre-1957, and it's attributed to a gentleman called Appleton. And they're referred to as the equatorial anomalies, or the Appleton crests, or the Appleton anomaly. But this generates density gradients that lead to irregularities that we won't talk about. Irregularities lead to scintillations, which affect radio communications. And historically, the equatorial region, because of these gradients, has been a kind of difficult place to predict how good your radio communications would be. That has even impacts on GPS guidance. Okay, the next electric field, then, we've just talked about that one at the equator, is at high latitudes. Our coordinate system changes. In the high latitudes, you go to a polar diagram with the magnetic pole at the center. Noon at the top, 1800, 6, and over here 0. Midnight, okay, a magnetic latitude. The magnetic frame is used preferentially when you're talking about the ionosphere and the magnetosphere. Okay, so here you have lines showing E cross B drift directions. In the polar cap, the plasma flows from noon towards midnight. Most of the time, there are exceptions, depending on the interplanetary magnetic field. If you take this and map it all the way out to the equator, equatorial plane, to the night side, which direction is the plasma flowing in the equatorial plane? This is flying anti-sunward. And if you were to map this all the way out, which direction does this correspond to in the magnetosphere? We talked about that in earlier conversations with substorms and other, but it wasn't from an ionospheric perspective. This is now strictly an ionospheric perspective of what we've talked about last week. Which direction are we flowing if you're proton in the tail at 20 RE? Towards where? Earthward, that's it. So this maps, this electric field from here to here, from dawn to dusk, maps out into the tail to that cross-tail potential they talked about. Several speakers talked about it. And experimentally, it does look like this. You know, that inside what's called the polar cap, your magnetopause boundary, open-closed field lines, you heard a number of terms like that used. This is the circle here. And the return, if you like, the current closure, leads to this particular potential, equipotential pattern in the ionosphere. This historically was kind of first observed with satellites in the early days when Earth, kind of LEO, low Earth orbit satellites crossed the polar cap, measured electric fields. Actually, electric fields are plasma drifts. But this pattern is critical. Storms modify it. Really big storms increase the diameter and the cross-tail potential. Typically, the cross-tail potential here might be 30 to 60 kilovolts. During extreme times, it goes up to 100, maybe not quite 200 kilovolts. And the plasma flows in the ionosphere are anything from tens of meters per second anti-sunward to almost a kilometer per second. And these numbers are tiny compared to solar wind speeds, where we talked about 300 kilometers per second and larger. So the flow speeds in here are relatively small again compared to elsewhere in the magnetosphere and in the solar wind. Okay, this region is called the cusp. This is the polar cap. And down here there's a discontinuity called the Harang discontinuity, where these equipotentials attempt to reorientate themselves at lower latitudes. This lower latitude region, of course, is what we call the closed field lines. Okay, this is just a repeat of what you've just seen, but to demonstrate experimentally, here's two satellite passes, and the vectors drawn on here represent the ion E cross B drift measured in situ on the satellite. So the electric field that we've inferred to be there really is there. These electrons and ions are E cross B drifting as these contours would kind of predict. Okay, that's the, if you like, the starting place for large-scale three-dimensional modeling. To put the ionosphere together, you could argue just have sunlight and everything co-rotates. But in actual fact, the entire system, when we talk about the heliophysics, where the sun is involved in driving this system, it's through this electric field pattern and the auroral precipitation that goes along with it, the aurora, that generates our true ionospheric complication. Okay, this is the plot I was looking for earlier. These are three profiles of electron density in the nighttime ionosphere. So the peak is sitting here above 200 kilometers, but a little bit below 3. There's A, B, and C. B is the one in which there is no E cross B. It's just the normal quiescent E cross B, you might argue. C is for a very large E cross B in one direction, and the direction is the direction such that this profile got raised. And when it got raised in height, its density also increased. The other one is where the E cross B drives you downwards. Well, sure, it drives you downwards, but the other really important thing is the density is decreased. Can anybody tell me why an upward wind leads to increased density, whereas a downward wind leads to decreased density? This is a very fundamental aspect of living in an ionosphere that has to be in an atmosphere. Recombination, okay? If you drive this plasma downwards, what can you tell me about the neutral density relative to what it was up here? It's increased, right? And by increasing the neutral density, your recombination rate goes up, so the density decreases. Over here, if you lift it, okay, and you're in sunlight or there's ionization going on, you're into a region of rarefied neutral gas. Your reaction rates have all gone down for recombination, but production is pumping you up so that you end up with much higher densities. And this is kind of why these winds and electric fields are so important, that they control not only the height of the layer, but how dense or otherwise it is. And simplistic as it might sound, having the wind fields done correctly and the electric fields done correctly are still far from being perfect in our models. Okay. The other little problem that occurs when you have an electric field, 0 in this case, and 100 millivolts per meter. This is a very large electric field, but not uncommon. This is kind of an extreme comparison. This is our ionosphere, let's say, in an auroral region. We have our peak, O+, and lower down you have your moleculars, our O2 and NO+, and here's your electron density profile. So this would be our reasonable representation of the aurora. But if you also have a very large electric field, not only will it raise or lower things, but unfortunately chemistry comes in. Because of this large electric field, there's heating going on. The plasma temperature changes, the electron temperature changes. As a consequence of that temperature change, the chemical reaction rates change. And all of a sudden, O+ is no longer dominant, and it's NO+. So a very simple reaction, which is O+ colliding with N2, the neutral molecule, leads to NO+ and neutral oxygen. So it's a very simple reaction, but its reaction rate is highly dependent on temperature. Temperature depends on how strong the substorm is, the storm is, and how localized. So the profile shape changes completely. This looks more like that Martian profile, only it's NO+ that's dominant, not O2+. And O+ is lesser than either of these. Okay, so the chemistry always plays an important part in an ionosphere. Okay, we've gone through, I've taken about an hour to get through what I would call the fundamentals. Now, all of these things have to be included in a real model, a three-dimensional model. And what we're going to do now is skim through outputs from various model calculations. CTIPI is the one that we're going to use mainly. CTIPI, Tim Fuller-Owl's team has developed this. It's a coupled thermosphere-ionosphere code with a plasmasphere in there too. So what we'll argue is what I've talked about are the individual processes. And if you go into the literature more than 20 years ago, you will find them extensively described in individual papers, one process at a time. But in a systems problem like the ionosphere, and I believe it's true in the magnetosphere and the sun, it's not that you can separate out one process. And when we talk to you often to make the conversations easy, we talk about one process, our favorite process, the one we think is dominant. But rarely is one process dominant in these coupled systems. Okay, so the idea of just assimilating the results of many separate processes is not a good approach. So let's just look at, if I'm in something in some of the D region, the lower thermosphere, mesosphere, E region, F1. So F2 at the top I haven't even put into this diagram. Look at all the different things you have to worry about as drivers. If you can argue, I know the chemistry reaction rates, I know my neutral gas, I can put this 3D model together. You have to get all of these things right in order to get the right answer. The sensitivity to any one of them needs to be determined in some way. Okay, so it's non-trivial, and put in color. Color's great because everybody says, oh yeah, wow, it's great, right? You look at this, and this is the problem in a nutshell. And Joe Borofsky at Goddard created this. In this one, it's not to scale. But if you're an ionospheric physicist, it is to scale. This little thing over here is pretty far away. Yeah? So we've put it in a scale of physical significance to an ionospheric physicist. You notice the magnetosphere, it's away over here somewhere. Yeah. So this diagram shows what we ionospheric modelers attempt to put together. Many of the words you might not have come across yet. We haven't talked about gravity waves, solar-driven tides. You know, if the sun heats up the day side, there's a pressure bulge, and the word pressure, gradients in pressure, lead to all kinds of interesting things in the magnetosphere and the sun and elsewhere. True here also. It drives the neutral winds. Here's this picture, the two-cell pattern, what we call a simple Voland. Our Aurora runs around here, so it's kind of schematically worked in. At low latitudes, there are dynamo-driven electric fields, and dynamo in this case isn't a solar dynamo. It's a dynamo in the mesosphere-thermosphere, where because the neutral gas is flowing, pushing ions and electrons around, you get current set up in the E region. When we talked about yesterday, David talked about electrojets. Okay, there's equatorial electrojets, but there's also the ones he was particularly referring to, the Aurora electrojets. And looking at these patterns, you know, an east-west seems the most logical way of significant electrojets flowing. But in actual fact, it's not that simple, as he pointed out. The north-south electrojets, or the distortion in this nice circular Aurora oval into loops and folds occurs. And that's where Eric Donovan's movies showed you it's not this nice, simple, fat piece of glowing light in the sky. It's not a rainbow. It's very structured, and all of the electrojets mimic that in some way. Okay, I could talk to this forever. You know, this is the good stuff. So let's kind of proceed. Our two-cell pattern in the real world gets very complicated. Okay, here's these little cells, but now here the whole ionosphere is rotating too. It's called co-rotation, and depending on your reference frame, there is this electric field that you'd argue makes the plasma co-rotate. You combine these two electric potentials, co-rotational and the magnetospheric, and your Voland two-cell becomes something like this. Okay, so fair enough, but in here comes the next major structure in the ionosphere. It's called a stagnation point. If you look at the convection, if you like, or the transport that's going on around, there's a point here where in this local time region, plasma appears to be stationary. If this is true, then if you're in winter and the terminator, the shadow, if you like, where sunlight and darkness appears, is up here. This point is always in darkness. There's plasma that hardly ever gets ionized other than through auroral processes. If you're in summer and this terminator is down here, this is all sunlit and this is dark, well then that's okay. But there's a complication. I've drawn terminators here. This isn't just winter and summer. The alignment of the magnetic pole and the geographic pole, how far apart are they? In the northern hemisphere, how far is the magnetic pole tipped away from the geographic pole? Yeah, 15 in the southern hemisphere, more like 11 in the northern hemisphere. But 11 means in a 24-hour period, there's an oscillation of 22 degrees. 22 degrees means, although I labeled this winter's equinox summer terminators, on any given 24-hour period, this line, which brings photoionization into the ionosphere in this coordinate system, wobbles plus or minus 11 degrees. In equinox, plus or minus 11. So look at this. This is a trajectory. We followed one piece of plasma for 24 hours, making all these loops. In winter, if the pole oscillates, then this terminator pops in and pops out. So the actual ionization that's going on depends on this motion of the Earth. There's a diurnal effect, as we call it, not just the Earth sitting there being ionized at high latitudes. And this plays another complication in terms of where are there high density features, low density features, where are the conductivities high and low. these all have a kind of diurnal dependence. This trajectory here, it's a 24-hour trajectory. It never got back to the beginning in 24 hours. The transport, if you like, got stalled over in this sector, and it just sat there for relatively long time periods. And if you're in darkness, then if this is the terminator and you're in this sector, your plasma goes away almost. It decreases through recombination processes. So by the time you get in the polar cap, you've got almost no plasma. So the dynamics, if you like, of even the plasma density is simple in one sense to hand-wavingly describe, but to put together in a dynamic sense has been very difficult. Okay, this is a C-Tippy. It's a neutral atmosphere representation here. The thermosphere at Z equals 2. This is the pressure level 2. It's 286 kilometers. So it's near the F region peak. And what Tim Fullerell's model is showing, latitude in both cases and longitude. But in his world, he still likes to use the geographic coordinate system. So things are kind of, you can always do transformations back and forth. But what you see here is what you would call temperature distributions, the hot sunlit part of the atmosphere, and then the pressure bulge that drives the neutral winds. So this would be a kind of simplistic neutral wind system. But up here, where you go into darkness and conductivities change, you get relatively larger neutral wind flows. And we'll come back to that in a second. So let's go one more. The plot that you just saw could be for a particular set of conditions, but this one then contrasts two sets of conditions. So what you have here are the vectors show how the neutral wind is flowing, and the colors show on a temperature scale what the temperature is. And again, it's where is it? Pressure. It says 12, but I can't believe it's pressure level 12. Sorry, I don't think it means 12. It's up in the F region, so I think 12 isn't correct. But basically, this coordinate system is 19 hours to 16 midnight is around here. And what you're looking at is the thermosphere under quiescent conditions. You've got a gentle flow towards the equator. This is at night, so there's not much happening towards midnight at the equator. But over here, you're in a disturbed condition. And because of the Joule heating that's been pouring into the atmosphere, that's your ionosphere neutral gas interactions, you get phenomenal amounts of heating at high latitudes. And as a result, the winds are dramatically changed from the quiescent conditions. And these winds, remember, affect the ionosphere, so that even although this might just be a neutral gas, the results of these dynamics, the changes in temperature, all lead to ionospheric changes just through the chemistry and the simple vertical drift that we talked about. As we kind of had talks during the week, different speakers talked about energy flow. And that's also true in our system. You can parse it out a little bit and look to see where the energy is going. So for example, a good or a major storm might bring in from the magnetosphere 500 to 1,000 gigawatts. Okay? We know about the two kind of basic drivers. One is Aurora. This is the particles coming down. And the other is the electromagnetic energy. It could be Poynting flux. I think Dana talked about Poynting flux with rather special reverence to Poynting. In our case, you've seen the E cross B patterns that we want to set up that are dynamic. So the energy coming in is parsed initially. About 20% or less goes to the particles, and over 80% goes to the Poynting flux, the E cross B. This energy appears or redistributes itself in two different ways. The Joule heating versus the kinetic energy. This one basically, through ion drag, drives the neutral winds. This is a really neat kind of thing to see happen. It takes hours for it to be very effective, but as the plasma flows across the polar cap and is driven by E cross B up to almost 1 kilometer per second, the neutral gas, which is usually only moving at in the polar caps at 200 meters per second can almost be pushed, if you like, by these collisional interactions up to 800 meters per second. Not quite the full E cross B velocity. And that leads to another dynamic effect. You've got this huge neutral gas now moving across the polar cap, and the aurora subsides. You've suddenly got a reverse, it's called the flywheel effect. This dynamic gas is now the driver and will generate electric fields that technically, to use the word drive the magnetosphere isn't quite right, but the idea that this energy stored in this flywheel, this neutral gas motion, can then be coupled back to the magnetosphere. It only occurs in very special conditions where there's a very marked decrease in geomagnetic activity over a very short time period. Okay, this is our standard joule heating. The energy is pure, what you call thermal energy. It leads to heating of the gas. Pressure gradients are created and new wind systems. In here, as you heat the gas, composition also can change. This is the same over here. You ionize, air glow, auroral emissions. Okay, so that's the energy picture. I've got 3 or 4 more, and we're doing pretty much well on time. I'm going to show a couple more, and then we'll call it a day. This is an example of, we've got about 16 days of data. And the data is such that this time period in 2005, January, there's a very nice, large geomagnetic storm occurred. Okay, and I'll just walk you through it to see how we kind of look at these things. What we've got up here is observational and modeling data together. Okay, we'll come back to that in a second. But in terms of our input function, how much energy came into the system, up here is the auroral particle precipitation. These are hemispheric averages, so it's kind of added all together. How much energy, not average, the total hemispheric power input. So for this storm in here, geomagnetic storm, we almost got 200 gigawatts from the aurora. That's the particles that leads it to visible light. But the joule heating, okay, in our 2 hemispheres, northern hemisphere and southern hemisphere, are up almost 1,000 gigawatts. So that comes back to what we talked about on the earlier slide, this 20%, 80% kind of distribution. So this is a Poynting flux energy. This is the kinetic energy. This is an attempt to understand the motion of the neutral gas, the change in it, if you like, coming up to 20 gigawatts during this time. And then down here, okay, so I have one more question. Remember we looked at the atmosphere. NO was never on one of the thermospheric slides. NO is a great contribution because it cools this whole system. Molecular atoms, nitric oxide, carbon dioxide. It's got vibrational modes. These vibrational modes are great at radiating in the infrared. So these are IR coolers, infrared cooling. So if there was NO or CO2 at these altitudes, the collisions with other neutrals leads to these vibrational states being excited, and then they radiate out. And much of it's optically thin up there, and the heat just leaves. So that they actually are the agents that cool down the upper atmosphere. And the NO, it's not a native species, if you like. It's created through aurora or high energy precipitation. So that it's a chemically generated species. After a few days, its density diminishes. It needs to be kept there. Fortunately, at the present time, there's not significant amounts of CO2 at our altitudes that we're talking about. However, it is CO2 that's the telltale sign of climate change. So there's been lots of attempts to study the E region, the D region, the mesosphere, this upper region, to look and see if the effect of cooling from these kind of radiators, if you like, is increased significantly over the last 50 years or so. Okay. I'm trying to decide which of these. Okay, I think we'll stop. We'll not stop here, but we'll talk about this one next. This, well, okay, I think all of you recognize the continent, the same continent twice. This is actual data, quiet times and geometrically very disturbed times. This is our GPS world. The GPS is used in different ways. Airplanes over the United States kind of fly in much closer corridors because of GPS. There's a thing called the Wide Area Augmentation System that the FAA has sponsored. And our airplanes that crisscross the country, there's always been more airplanes than, let's say, comfortable zones in which you would want to fly. You know, there's just a lot of people flying. Anyway, to cut a long story short, about 15 years ago, the FAA decided that GPS geolocation, as you know, is fairly accurate, 10 meters, 50 meters under bad times. So for airplanes that are kilometers apart, that seems a very reasonable compromise. So that airplanes using this WASS system, as it's called, can actually fly across the country, knowing exactly where they are to, let's say, 10 meters. Anyway, this is quiescent times. This, what you're looking at, is a thing called TEC. What does TEC stand for? Total electron content. This TEC is the worst problem for GPS. If the number of electrons in the path between your receiver and the satellites that transmit the signal changes, then the correction, if you like, the delay for the signals to get, the phase in which it arrives, messes up the calculation. So they, what you might call the noise for the GPS system is this electron density integral. It's the best thing for us ionospheric people because we get to learn about the dynamics in our ionosphere. So this is a plot under quiet conditions, March the 30th, 2001, of what we would infer as the TEC, total electron content over the United States. This is where things went awry between about 2001 and 2005 or so. There were a large number of very large storms, the Halloween storms, Bastille Day. During these particular times, this picture became like this picture. Large structures of TEC enhancement appeared with depletions in other places. Now, on their own, it's not a problem, but what happens is there are very strong gradients in TEC. And the way GPS works is you have a receiver that's looking in different directions at different satellites, GPS satellites. And it's got an algorithm that relies on some representation of the ionosphere. And most of these representations are relatively homogeneous. They have day-night and terminator effects, so that's okay. But the problem really is that during these particular periods, the gradients are such that your GPS signals are coming through quite different TECs. So the simple algorithm on board is generating errors. And the WASS system, in order to protect itself, the minute its algorithms realized, hey, I'm getting solutions, but I can get a range of multiple solutions depending on which satellites I use, kind of pointed out to the user, I'm not going to give you an answer because I'm worse than 50 meters. And it goes offline intelligently. However, now your airplanes are flying no longer with knowledge of where you are. Well, obviously they know where they are, and other methods can be used. But the whole point of the WASS system was airplanes have been brought much closer together. So the danger levels, I mean, they're not so close that they're touching or anything, but relatively speaking, they're much closer. So for hours, in fact, in one example, almost a day, these structures over the mid-latitude, this is not even the auroral zone, this is not up at high latitudes, it's over the United States. It pretty much shut down the entire system. And of course, from an engineering point of view, you can put more methods of collecting information so that if you have more ground-based sensors, this WASS system, which relies on understanding what structures are currently there, you can make corrections, and that's how the WASS system works. So by putting out more receivers and real-time networks, the problem got more complicated, but there were what I call engineering bootstrap solutions. Now, clearly, as a modeler and a theorist, we think we can model these things. And when I say we think, all theorists think, and therefore we're still a decade away from getting these structures correct. Okay, this is another variant of demonstrating the same thing, only over the whole American sector. Here's South America, here's North America, and remember over here there's a special region, the South Atlantic anomaly. The magnetic fields are different. Very few of our models build this in correctly. Here is what's called the equatorial anomaly enhancement. During large storms, it's enhanced here and here. In the northern hemisphere, it's much more complicated with this structure again across our American continent, if you like. This just represents yet one more version of these storms. And these are all, each one of these little boxes represents reporting from one ground-based GPS receiver with an inferred vertical TEC. Remember, a GPS receiver sits on the ground and looks at different angles. So it very rarely looks straight up at a satellite. So when it reports TEC, it's called an oblique or a slant TEC, and it has to be converted to vertical. But these maps, well, they're not complete. Why is there nothing over here? Oceans, okay? So deploying instruments is tough because there's a lot of water around, and it's hard to put these receivers. Buoys are being worked on that will carry GPS, but we aren't yet at the level of sophistication that we can populate these areas as well as these areas. Okay, I think I want to, one last. A solar flare. Okay, when we talk about heliophysics, we normally talk about, a CMA being launched. It travels to the magnetosphere. The magnetosphere gets energized. Energy is stored, released, and we talked about various methods of releasing that energy. The auroras formed, but that's 18 hours for the Carrington event, or 2 or 3 days is the typical delay time before our environment sees that. But in actual fact, that's not entirely true. A solar flare, how long does it take a photon to get to the Earth? 8 minutes. Okay, good. So 8 minutes after a flare, an X-class flare is launched. Okay, this data is not for the same time period as this, but over here are examples from the GOES satellite, which monitors, it's not currently, but for many, many decades, GOES satellites monitored the X-ray flux continuously in 2 different integral bands below 1 nanometer. So these are our X-rays. And the classification system is a logarithmic, it's a pseudo-logarithmic scale. But there's X, M, class, X being the strongest that we label. Over here is an X-class flare that occurred in 2003. And this plot that you're looking at is data from the CHAMP satellite looking at the neutral density through accelerometers. So that if the density changes, the satellite would sense an acceleration. And although it's very small, it is measurable with modern day technology. The satellite kind of more or less is in polar. It's not exactly. The flare occurs. Energy is deposited in the upper atmosphere instantly, but the thermosphere takes a little bit of time. So this is 1 day from here to here. So that over the duration of the flare, the atmosphere is starting to respond, and the drag on the satellite, if you like, is measured here by the density increase. Or the density increase leads to what was measured as a drag, the acceleration. And then, of course, once the energy is deposited, although the flare's gone away, the thermosphere is still hot, if you like, from that energy for several days. So that was kind of our skip it. Okay, I wish to stop now. Thank you very much. Since I've gone past time, I'm around so you can talk to me, but I think we should break in order to keep today's kind of moving. Dana, Amitav, is that okay? We'll just break.